Okay, that was unfortunate. I believe the recording stopped by itself, but it doesn't matter. Let's go back. So what we said last time, we said that v-bit is 1 bit and d-bit is 1 bit, and tag is 26 cents. We took it from the previous question, which is question A, and data is going to be the number of words, right, in a block, and then times the word in bits. Yes. So we have 4 words in a block. We have each word is made of 4 bytes and each byte is made of 8 bits. So 4 times 8 times 4, because 8 bits times 4 bytes, because one word is 4 bytes and one byte is 8 bits. Multiply them and then multiply them by 4, because we have 4 words in a block, and then we get the data. Or you can just take the shortcut that I just created, find the number of words, and always multiply them by 32. Sometimes it's going to work, sometimes it won't, because there might be some changes in question. Okay, now what we can tell here that they didn't ask what is the total size, set size, and total set size is very crucial because we're going to need it in order to find the SRAM size in bits. Maybe we got lucky this time because they didn't ask, because the set size is actually the same as block size in bits. This is the total set size in bits is the same as total block size in bits. But maybe the next question they're not going to be the same. So SRAM, we're going to get SRAM wrong. We're going to get total set size in bits wrong, and we're going to miss some points. So let's get back here. We said that total block size in bits is 165 bits, and we said that total set size is the total block size in bits times how many sets do we have. Times how many blocks in a set do we have, and we said that we have one block in each set. We have 4 sets: set number 1, set number 2, set number 3, set number 4, and we have in each set one block. One block multiplied 165 bits is going to give us 165 bits, and this is the total set size in bits. Finally, we're asked, not finally, the third step, which is the SRAM size in bits, is going to be number of sets times set size in bits. We already got the set size in bits as 165. We're going to multiply it by 4 since we have 1, 2, 3, 4 sets, right? So 4 multiplied by 165 is 624 bits. Remember, you wouldn't be reaching this far without drawing this thing, or this graph. This graph is very crucial to understand what's going on. And it's also going to help us in question C, and I'm pretty sure in question D in part A. Finally, we reach what is cache memory total data field size in bytes. And this is a very tricky question, because you might be saying block size here is same as total block size in bits, and this is wrong. Block size is something, and block size in bits is something else. Going back to our problem, which is which is cache memory total. I don't like this color. Yeah, okay. Cache memory total. We have set size, and we said set size is 4, where it's already mentioned up here. Number of sets is 4. You can, number of sets. This is can be called as set size. Yeah, good. This is can be addressed as set size, and it also can be addressed as number of sets. Yes. And n, we already said n is 1. How do you know that n is 1? We said when n is 1, n means number of blocks in a set. And as you can see, one block in one set means that n is 1, because there is only one block in any set. And then block size. Remember, we got this as in bytes. In bytes. So what is block size? Block size is how many words in each block. Correct? Correct. So how many words we said? Oops. Oops, 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 oops. Okay. How many? What the hell? What's going on? Okay, I don't know what happened, but we already said that. We already said that block size is, as you can see, block size is 4 words. So we have 4 words, right? So it should be multiplied by 4, but this is not enough because we know that each word is 4 bytes and we want our answer in bytes, so we multiply it by 4. So the total answer is going to be 4 times 4 times 4, which can be also addressed as 4 power 3, which is 64 bytes. Ta-da! And this is the answer of cache memory total data field size in bytes, which is 64 bytes. And we are officially done with part B. Okay, going to question C from question 1 part C. It says show the final contents of the cache memory in a figure in terms of its subfield whatever. Give the values of tag, exit, extra, and bits show block data contents in terms of M1, M2, etc. Okay. Alright. In this part, we're gonna need the table that we were given in the beginning, and we're gonna need the main memory in bits structure, which is this. Which is this: byte offset, word offset, index, and tag. Remember, index is for sets, word offset is for block. No, not blocks, sorry. Words. And byte offset is given already. And tag is for tag, so I don't need to write it down. Okay, back to business. We said step 1 memory content and right next to it the memory address in binary. And you might be like, so what does that mean? So this is basically is to take M1 and write it down here. And then you take the corresponding memory address in binary, which is this number, and write it down here. Alright? So I'm done with this step. What are the next 2 steps? I'm not gonna write them down because I don't have enough space, but I'm gonna explain them in a very easy way. So let's start from the beginning, which is from the least significant bit, which is this one, right? We already know that the byte offset, let me change the color. We already know the byte offset, let's take blue, I guess. The byte offset is 2 bits, right? So these 2 bits are for the byte offset. And honestly, these 2 bits are useless. We don't care about them. Then we get the word offset, which is also 2 bits. So these 2 bits with another color is going to be 2 bits, and we also don't care about them. Now we go to the most important part, which is sets. Remember, we already said that we have 4 sets, which is, I don't need to change this, but like, which is this table. I'm gonna drag it. I don't need to drag it down, but like, here is the table. You can take screenshot of it because we're gonna need it a lot to solve the next questions. But now you need to know that we have 4 sets, which is 0, 0, 0, 1, 1, 0, 1, 1, and these are the these are the bits of the set, which is with another color, and it's gonna be a magnificent color, which is dark green. I love it. It's gonna be 0, 0. So basically, the set we're using is 0, 0 in this example, of course. Down there, 0, 0 is the same as this one, right? And then we got the tag, which is 26-bit, which means the rest is going to be 26 bits, which means this is the tag. Let me write it in a bit. And basically, you're just going to do the same with literally every memory content, M2, M3, M4, M5, M6, M7, and you're gonna write the corresponding memory address in binary, and then you're gonna say what is set and what is tag. You remember, the most important part is set and tag, and in order to reach them, we need to know how many bytes of set we have, how many word of set we have, so we can skip in order to see where does the set location is located in. Okay, finally done. As you can see, all I did is I changed the tags, or like the bits that's in tag with a magnetic color, and the bits that's in a set with dark green color. And to the next step, which is going to be so annoying for me because I'm gonna draw a lot. I mean, on a paper it's easy, but in a computer, nah, it's hard. But here is the next step. First of all, you're gonna take M1, and then you're gonna draw a table, right? You're gonna have 1 1, 1 0, 0 1, and 0 0. And if you didn't figure this out, it is literally the same as this one. So it is literally the cache memory. This is actually this is the cache memory. You know, if you didn't know, this is the cache memory, and we're gonna draw it again, but like in a small way. Why? Here is why. We're gonna have 1 2 3 and 4, and M1 is actually in set 0 0. So yeah, okay, after fixing it, yeah, it's too big. It should be very small actually, because you don't have enough place in the exam, but it should be too small. So after you have done this part, after you're done with this part, all you have to do is to have the cache and to put the data inside the cache. So we got M1, which is memory content M1 in set 0 0. So we're gonna take this M1, we're gonna copy it, and we're gonna put it in set 0 0. And this is step number 1. Step number 2, literally do the same. You see this, copy, paste, and copy and paste next to it, to any place for you. Change this M1 to M2. Oops, sorry. What should we do? Yeah, M1, M2, and then M2. And then go check M2 here. It says set 1 0. Set 1 0, M2, write M2 here. And so on. I'm gonna continue, and I'm gonna stop when I face a problem. Okay, I didn't find any problem till now, but like I'm gonna explain what I'm doing. So basically, I'm just putting the data, which is M1, in cache memory. So M1, the set is 0 0. I put it here, right? And then M2, it is in 1 0. So basically, it won't affect 0 0, or it won't affect what's inside the set 0 0. So I keep M1 as it is, and I just pop I just put M2 in 1 0, which is the tag of the set, and I do the same with M3 in 1 1. Now remember, each set has a different tag. As you can see here, 0 0 0 1 0 0, and M2 is 0 0 0 0 1 0, and so on. These tags are very important in the future, and we are gonna say why. So basically, why do I have M1 here, M2 here, M3 here? This means this table is belonging to M1, and we're going to tell you where we put M1. This table is belonging to M2, and we're going to tell you where we're going to put M2, and so on. Okay, now for the first problem. It's actually not a problem, but like it's a thing that you need to pay attention to. We have M5, right? We reached step M5, and we have table M5, but we didn't write M5 yet. So where should we be looking? You're absolutely right. We should be looking at the set number, which is 0 0. So, and we said that each set has one block, and one block has 4 words. So M5 can go with M1, since there are 2 words out of 4 words. But this is not the problem. You know, before we put anything in a set, we need to check its tag number. If the tag is the same, then we put it. If the tag is not the same, then a conflict miss will happen. I'm gonna explain conflict miss and compulsory miss and capacity miss in part D, since we are in part C at the moment. So basically, we want to put M5 in set 0 0. So we look at its tag. Its tag is 0 0 0 1 0 0. Now we see M1 because it's in 0 0 set, and we check its tag. if they have the same tag, which is 000100, and they actually do, all we have to do is put M5 inside. If they don't have the same tag, then a conflict miss will happen or a compulsory miss. I'm going to explain when compulsory miss happen, and I'm going to explain conflict miss will happen when happen. Yeah, so basically all we have to do is take M5, Control C, Control V, put it next to M1 just to make it neat. I'm just gonna separate both of them, and here we go. We have a beautiful table. Now continue with M6 and M7. Okay, so I have done M6, or like let's say data number. Yeah, M6, which is the content of the memory, M6, and it went out pretty well. It had the same tag number as M3. It has the same tag number as M3, and M5 has the same tag number as M1, and they both had the same set number. So I ended up having M6 with M3 and M1 with M5, and life is good. Now we check M7, which is the last thing. First of all, as we usual, we look at the set, which is 1, 1. So basically it should be here. But before we put it here, we need to check if the tag is the same, which is 1, 1, 1, 0, 0, 0. Oh, there is something different. We don't have the same tag set. They are not equal. As you can see, the difference is 1 here and there is no 1 here. So is this a conflict miss or a compulsory miss? Well, let's start explaining compulsory miss and conflict miss. Okay, as you can see, I wrote it kinda in a bad way, but I hope it makes sense. A compulsory miss happens, oh, this should be happens when you access a set for first time in a new tag. So basically, this is a compulsory miss because it's a new tag and it's first time accessing this tag, right? This is a compulsory miss as well. And this is also a compulsory miss. This is also a compulsory miss. But when we reach M5, is it a compulsory miss? No, it's not a compulsory miss. Why? Because we have the same tag and we have the same set. If set was different, if we had the same tag but with another set, right? Then it would be a compulsory miss because we didn't encounter any set in the same tag before, all right? But since we encountered the same set in the same tag, then this is gonna be hit, and I'm gonna write hit in a light yellow color. M6 is the same thing since we accessed the tag before 000011 with M3 000011. Are they the same sets? Yes, it's 1 1 and 1 1, so this is a hit. Now, is this a compulsory miss or a conflict miss? Well, coming back to conflict miss, we have the definition says it happens when sets bits are same but with different tags. But I should have written this in a red color, and I will write it in a red color and come back. Okay, but a compulsory miss must have happened first. If not, then it's a compulsory miss. Well, did we access this tag before, which is 000111? No, we didn't access it first. Then it's a compulsory miss. And therefore, we have 1, 2, 3, 4, 5 compulsory misses and 2 hits. So basically our miss rate is 5/7. But actually this is not asked because in part C they just asked you to write the following. Show block data contents in terms of M1, M2 and give the value tags. We already have done this and show the final contents of the cache memory, and this is literally what you I'm not done yet, I'm so sorry. Well, since a compulsory miss happened and the tags are different, we're gonna delete M6 and M3 and we're gonna put M7 instead of them since it is the newest thing, it's the newest data with a new tag with the same set number, which is 1 1. And yeah, this should be your final answer. This should be your final table, I believe. Well, forget about what I said earlier. We are not done with this thing yet, since we need to show the final contents of the cache memory. And this is gonna take like a bit long to draw, so be right back. Okay, I wrote the table. I'm not sure if it should be looking this way or not, but I'm gonna discover it by the time. So basically, here is going to be the v-bits, since they asked me to draw the final content of a cache memory, which is, so here is going to be the v-bits, right? Oops. Yeah, here's good. Let me take it and put a d-bit over here. Hello, why is it blue? Okay, take it and then write it here and then bring it here. Let me do it and come back. Okay, I'm back. Well, this should be our table. It contains vbit, dbit, tag, and contents. What should I be writing here? It's pretty easy. I'm gonna write M7 because as you can see M7 is here, and then I'm gonna drag it to contents because this is where it belongs. And then what is the tag of M7? I'm gonna look at the tag from what I have done here in step number 1, which is 000111, right? 000111. I'm gonna take it and I'm gonna put it over here. Alright. Now, what is dbit? Remember when I was here and I told you dbit is when you literally store word? So all you have to do is go back and you check it. Does M7 store word? Yes, it does store word. So dbit is gonna become 1. So basically I'm gonna write 1 over here. Yep. It's dbit. Alright, what is vbit? Vbit means that this set is accessed. Did we access this set? Yeah, we did. I mean, like, we put M7 inside it. So 100% we accessed it, right? So we're gonna write 1. Cool. Now, we do the same with the following steps. So we're gonna take M2 over here and put it over here. And then we're gonna look at the tag of M2, which is this one. We're gonna copy it, and then we're gonna put it in text section, I believe. And then we're gonna look if M2 is, oh, we do have the picture over here. I didn't notice. M2 is a store word, so yeah, I mean, dbit is 1, and come on, it's accessed, right? So vbit, which stands for valid, which means that this set is valid because we accessed it. It's good, it works. Now, what about M4? We're gonna take M4, we're gonna put it here, we're gonna take its tag, and we're gonna copy it, do the same steps. Nothing is new so far, everything is fine. You can do this, I guess. Now we check the dbit. Is M4 store wording? No, it's not store wording, it's load wording. So basically we're gonna write here 0 because 1 is for store word, 0 is for load word. Or it's not like this actually, it's basically when you write something inside the memory, the dbit becomes 1. That's it. So when we store word, we write something inside the memory, and therefore the dbit becomes 1. And is v bit 1? Yes, it is. We access this set, so basically it's 1. Last and final, we have M1 and M5 in the same place. So what do you think we're gonna do? Yep, we're gonna copy them and put them in the same contents. Then since they share the same tag, I believe they do share the dbit, and I believe they do share the vbit. I mean, vbit is 100% shared, but tag, it's 100% shared, but you don't know if dbit is shared or not. So basically, you go to tag, you take their tag, any one of them is fine because like the tag is literally similar. 000100, which is literally the same as 000100. And you put it here, and you check M1 load word, M5 load word. So D bit is 0. And V bit is 1. Oof, long solution. And this is basically the solution for part C. I know it's long. Take it easy. It's not a big deal. It is just like drawing and working. And once you understand this concept, I believe it becomes easy and fun to solve. I hope so. Okay, finally, last question. And actually, it is the easiest. It's not the easiest, but you know, since we understand and solved the previous questions, we were able to reach also the answer of this question before we even read it. For each memory access, indicate if it's a hit or miss. I mean, oh my god, not the same mistake. Okay, yeah. I mean, we have solved this, didn't we? Look, we indicated that the blue lines are for miss, and we indicated that yellow lines, which are these ones, are for hits. So basically, we have 7 data, and we have 1, 2, 3, 4, 5 misses, so it's 5/7. I hate this program. And now it says give the mistype. We already indicated the mistypes, conflict and capacity. Well, capacity when, let's say, okay, let me give you an example about capacity. It's very easy. Let's say we have M1, M5, M8 and M9 at the same place here, right? So we have M1, we have M5, and we have M6. No, sorry, M8, because M7 and M6 are already taken. And then we have M9. Cool. So how many words in this block, or in this set, sorry? How many words? Yeah, how many blocks in this set? We said 1 block. And how many words in this block? We said 4 words. So what if we have M10? And it's also in the same tag and in the same set. Now this is a capacity miss. Why? Because it's already like the set is already full. There is nothing, we cannot catch more data inside it. So basically we just delete everything. No, sorry, we don't delete everything. We put M10 and we delete M1, since M1 was the least used bit, least recent bit. No, sorry, least recent data accessed. Least recent data accessed. Right? So we delete M1 and we put M10 instead of it. So now we have M10, M5, M8, M9, but like M10 is like going through M5, so it's a problem. All right, another question. What if we had M11, right? And this M11 is in set 11 and it has the same tag as M6. Will this be a compulsory miss or a conflict miss? It's going to be a conflict miss because we have already defined this tag and we have already defined this set before, and that time we defined it was in M3. So any mistake, oh yeah, it's gonna be conflict miss because M7 is different, it has a different tag, and M12 or M11 has another different tag. I'm pretty sure you don't understand what I'm trying to say right now, so I'm gonna draw it and come back to you. Okay, back. Now let's say I want to have this M15 inside my set. What am I gonna do? Basically, I will first look at the tag. Sorry, the set. Right? I said the set is 1, 1, so it should be going here. Right? Does it have the same tag as M7? 0, 0, 0, okay, and then 1 yeah, 1, 0. So they don't share the same tag. So basically, is it a compulsory miss or a conflict miss? We said it's not compulsory miss. Why? Because we have accessed this tag earlier, and the first time we accessed it, it's compulsory miss happened. So it won't happen anymore. So it is 0, 0, 0, 0, 0, 0, 0, 1, 1. And first time happened in here in M3, 0, 0, 0, 0, 1, 1, right? So it's not a compulsory miss. It's a conflict miss because the tags are different, but they have the same set number or same set bits. So basically what we're going to do now, we're going to delete M7 and we're going to take M15 and put it inside this set. I think now you are good with compulsory misses and conflict misses and capacity misses, right? Yeah, I hate this program. I can't do whatever I please. Okay, now I can do. It's weird. Okay, cool. It says give the miss type for each case. What is the hit rate? Alright. Give the miss type for each case. We already said that we have compulsory miss here, compulsory miss here, compulsory miss here. Hit, compulsory miss here. Oh, that's an extra example I gave, so you don't need to care to think about it. And it said what is the hit rate? It's literally M5 and M6 were hit among of 7 contents, which is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So it's basically 2 over 7. Alright, I'm stopping here and coming back. Okay, finally, last thing. I mean, as I explained before, M1 is a compulsory miss, cause tag and set are first time accessed, right? Compulsory miss, tag and set are first time accessed. M3 is the same, M4 is the same. M5 is hit because first time tag and set were encountered in M1, which means M1 faced the same thing that M5 is facing right now, right? So M5 is hit right now since we brought M1, and because of special locality, M1 brings its friends with it, and it seems that M5 is one of its friends, so M5 is hit. Same with M6. M6, uh, like its tag and set was first encountered in M3. And finally M7, I give like a little bit more details to understand the situation. Even if the set was accessed before in M6 and M3, as you can see, they have the same sets, M6 and M3, they have the same sets as M7, but the tag is newly encountered. It is as if we went to a new location. And since the tag is newly encountered, you can literally remove what was inside that set because we already accessed the new set, like as if we as we did here in where yeah, as we did here in this example, we deleted M6 and M3 in order to put M7. And that, what is the hit rate? Since we got 2 hits and we got 5, like the total is 7, the 7 memory content. So basically we got 2 hits, 2 over 7 is hit rate and 5 over 7 is miss rate. And that's it for everything. Thank you so much for watching. I hope you learned. This is only question 1. We still have question B. I'm gonna record it in another video without going through all these steps. I'm just gonna go through the new steps that might be very important and might be very affecting your grade. Good luck.